Feynman diagrams provide a graphic, intuitive, and useful way of expressing perturbation theory. These diagrams emerge naturally from the path integral formulation of quantum mechanics or from the path integral expression of the propagator. In particular, let's consider a Green's function. The Green's function is also known as the propagator. And I will denote it with the letter G, and then here we have the final state, xt, so t stands for the final time, and x stands for the final point. So we reach this point at the time t, and then here we have the initial state, which we label y for position, and 0 for time, so we start at time t equal to 0. This is a propagator, so it tells us how we start from a certain point and it tells us how the system evolves to the final point. We have a path integral to express that. So I have an integral from the initial point at the initial time, so we can label this in the following manner, y0, and then here we have xt. Here we have the measure of the integration, dx of tau, and then we have an exponential of I over h bar of the action. And if we have a particle, we integrate from 0 to t, and then we have the kinetic energy of the particle, mx dot squared over 2, minus the potential energy v of x. So we assume that in this case the particle is not free. We also have a potential energy to be more general. And we integrate over tau, so here we have an integral over tau, and then we close this square bracket. Now, when we do perturbation theory, we expand this exponential in the following manner. So we expand it in powers of the potential energy, like this. We have integral from y0 to xt, dx of tau, and then we have an exponential of I over h bar, and here we have only the integral of the kinetic energy, so mx dot squared over 2, and the integral is performed over tau, and then we have a summation. It's a series of infinite terms, j from 0 to infinity, 1 over j factorial minus I over h bar to the power j, and then we have integral from 0 to t of v of x. X is a function of tau, so this is x of tau. Remember that. And we integrate over tau, and then we raise it to the power j. Remember that this measure here is proportional to an infinite amount of the products of differentials of the kind d of x, dx of tau 1, dx tau 2, dot dot dot, dx tau n. So the integral is usually discretized so that the differences between these time values are infinitesimal. So the difference between tau 1 and tau 2 is infinitesimal, but when we discretize the system, we have something like dx1, so this differential will become dx1, this differential here will become dx2, and so on. So of course here n would go to infinity, and there is an infinite amount of differentials which are not really countable. But in order to calculate and make any meaning out of the path integral, we discretize it in such a way that we hope that we can find a finite result. Now, the first term in the expansion, which we can label g sub 0, xt y0, is equal to, now this is for j equal to 0, we get integral from y0 to xt, and then we have d of x, dx of tau, exponential of I over h bar integral from 0 to t mx dot squared over 2 d tau. Now it is possible to calculate this path integral because in this case we don't have the explicit dependence on the potential, and in order to do that we have to discretize the integral and we have to properly define the measure. In particular, when we discretize the integral, x dot will become the discrete version of the derivative. So we have something like xk minus 1 divided by some finite increment of time, delta t. So d tau will become delta t, or if you want a delta tau, in this case I'm calling the time variable t, and the integral will become a finite sum. So it's a summation, and it can be carried out. So as I said, this will be proportional, and the proportionality constant is related to, so it can be explained by means of quantum mechanics, but it can also be explained in other ways, so that we normalize the green function. I will say a little bit more about it in a moment. First, let me finish writing this. So that's proportional to dx of tau 1 dot 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 dx tau n. And in our case, tau 1 would be 0 because we start at time t equal to 0, and tau n would be capital T. But this is an infinite amount of differentials that they are not really countable. So we discretize the integral. This can be done. I have also explained it on other occasions. And what you get is something that is proportional to the exponential of Im over 2h bar t x minus y squared. And if we define the proportionality constant in a certain way, I will tell you a little bit more about it, but now let me try to give you the intuition. We get this constant, the square root of m divided by 2 pi I h bar t. So for now, this is just mathematics, but this constant, so this proper normalization, tells us that this green function, the green function of order 0, satisfies the following equation. In particular, it satisfies I h bar, partial derivative with respect to time, plus h bar squared divided by 2m d squared dx squared. This operator is applied to g0 of xt y0, which is equal to I h bar, so this constant. Then we have the Dirac delta of x minus y, and then we have also the Dirac delta of the final time t minus the initial time 0. So basically this is just the Dirac delta of t. Simple as that. So I will not go through all the steps, but the idea is that if you integrate this equation, and in particular you can do that, so the simplest way is to Fourier transform this equation. So you go from the variable x minus y to the variable p, then you go from the variable t to the variable omega. So you take the Fourier transform. Basically, you can define the function g of omega p, g sub 0 if you want, which is given by the integral of g sub 0 x minus y t. And let me tell you that this function here coincides with this one. Basically, with some argument, you can say that this function actually depends on the difference between these two values and also on the difference between these two values here. So you can write it like this. Then here you have some complex exponentials, e to the minus I omega t over h bar, e to the I p x minus y over h bar. You integrate over t, and also you have to integrate over x minus y, like this. And the inverse transform, of course, can be defined like this. It is a double integral of g0 of omega p. So basically, if you want to differentiate these symbols here, you can put the hat here to denote that this is a Fourier transform, and also a hat here. And then here you have e to the I omega t over h bar. So it's the following exponential with a plus. So you have to complex conjugate it. Then you have e to the minus I p x minus y over h bar. So it's the same exponential here, but with a minus instead of a plus. And you integrate over omega divided by 2 pi, and you also have to integrate over p divided by 2 pi. So with these definitions here, you can fully transform this equation, and then you can carry out the integration over omega. By means of the residue theorem, you will obtain a certain result, and then you can integrate over p. And the integration over p is performed over a Gaussian integral. And at the end of the day, if you do this, from this equation, what you obtain is exactly this expression here. So basically, by imposing the constant here, we are really imposing the constant here. So you can see that there is some kind of relation between this equation here, which is basically the Schrödinger equation if you check the left-hand side, because we have something, we have the Schrödinger operator, if you want to call it that. So this is the energy operator, whereas this is the Hamiltonian. So IH bar d over dt is a certain operator that we can also explain by means of energy, by thinking about fluctuation of energy, but let's not do it here. So this is applied to G0, whereas here, this operator here is minus the Hamiltonian of a free particle applied to G0, and then here on the right hand side you have some Dirac deltas that tell you basically that if x is not equal to y and t is not equal to 0, this would be 0, right? So it's as if we are setting this to 0, and so it's as if we are considering the Schrödinger equation. And it's the free Schrödinger equation because in this case, for j equal to 0, in the expansion, this is the free particle. So G0 is related to the propagation of the free particle. This is some intuition behind these concepts, but we can move on. We can consider also the term for j equal to 1, and in particular, I will consider the term, so when you consider j equal to 1, you have something that is multiplied by minus I over h bar. So I'm assuming that the term g sub 1 is what multiplies minus I over h bar. So let me just show you. It's easier to show than to explain in words. G sub 1 of xt y0 is equal to the integral from y0 to xt path integral, so dx of tau, and then I have the exponential of I m over 2h bar integral from 0 to t x dot squared, which is a function of tau, remember that, d tau, and then here we have an integral from 0 to t v of x, which is a function of tau, remember that, d tau. So we have this additional term in the definition of g sub 1 or g1. Now, in order to carry out this integration in some meaningful manner, what we are going to do is, of course, we are going to discretize this path integral, and we interchange the order of integration and path integration. So in particular, let me rewrite g sub 1 in the following discretized manner. So here we have the summation over j delta t, which is basically this integral here, discretized. So I'm putting this integration symbol outside of the path integral and discretize the integral. Then we have the path integral, so this remains an integral. So we have an integral over some products. So we have products of differentials dxi, I from 1 to capital N. And then here we have some normalization constants that I will not write. I will write as C sub I, not really important here. Then we have the exponential of I m divided by 2 h bar delta t. Remember that when you discretize the path integral, this velocity here, this x dot squared, is discretized as I explained earlier. So we get something like this: xk plus 1 minus xk squared. And if we want to obtain a velocity, we have to divide by the increment of time squared, but I have already simplified this delta t because this d tau will become delta t. So it's as if I have delta t divided by delta t squared, and therefore I have this factor of delta t here in the denominator. Then I have the discrete version of the potential, which I can write of v as v of x sub j, because x of tau will become x sub j. Now the integrals for k equal to 1, k equal to 2, all the way up to j minus 1, and the integrals from k equal to j plus 1 to n, they are just free particle integrals, right? Because we don't have to integrate also over this v of xj. When we do the integration over some of these values, for example, for I equal to j minus 1, the integral is performed only over this exponential, because you don't have to integrate also over this potential. You have to integrate over the potential if I is equal to j. So this is problematic because we don't have a closed form expression for that, because we have to integrate over the potential. We need to know what is the form of the potential in order to be able to carry out the integration, and we cannot do that. But still, we can try to understand something. And we don't need to carry out the integration, and we don't need to know the form of this potential to be able to infer some more information about what we are doing here and what is really going on physically and mathematically. In particular, g sub 1 can also be written in the following form if you think about it. So now I'm going back to the continuous version of the integral. So instead of having a summation here, I will replace it with an integral from 0 to t over tau. Remember that this summation is replaced by this integral here. And then we have an integral over some variable that I will call xi, and xi in the discrete case is x sub j. So this is a definition. As we go back to the continuous case, we let xj become xi. So we call it xi for convenience. And we can write g sub 0 x minus xi t minus tau v of xi, and then we have g sub 0 of xi minus y tau. And now let me explain a little bit more. So in particular, this propagator here, for example, is the same as the following notation: g0 of xi tau y0, and this would be g sub 0 xt xi tau. So let me explain it more clearly. In particular, this means that the integral here, as I said earlier, can be carried out quite easily if we go from I equal to 1 to I equal to j minus 1, because we don't have to integrate over this value. And the integration will give you something like this. It will give you a propagation. It will, let's say, explain. It will represent a propagation from the point y at time t equal to 0 to the point xi at the time tau. Remember the xi is x sub j in the discrete case. So it means that we have a propagation, a free propagation from this point to this point. Then here we still have v of xi, which is this v of x sub j in the discrete case, which tells us that there is something happening at the point xi. There is some interaction, and that will become more manifest later. But after that, we have another free propagation from this point at this time to this point at this time. Now, let me define the function g sub k, which is a generalization of g sub 0, xt y0, which is equal to, so this is the definition, 1 over k factorial integral from y0 to xt, and this is a path integral, so we have dx of tau exponential of im divided by 2 h bar integral from 0 to t x dot squared d tau, and then here we have an integral from 0 to t v of x of tau d tau, and this potential, this integral of the potential is raised to the power k. So actually this is not really surprising, because all these terms basically appear in the expansion that we wrote in here. So those terms are really not surprising. It's as if we are expanding this g, which is the total propagator, as a series of terms, so of the kind summation over j from 0 to infinity minus I over h bar to the power j g sub j of xt y0. Now let's try to understand a little bit more about the higher order terms, so these terms here, because we have already described g sub 0. So if you set here k equal to 0, this would become 1, and similarly the factorial would also be 1. So we have already explained g sub 0 and also g sub 1. We managed to find the formula for that in terms of g sub 0 and the potential, as you can see here. But what about higher order terms? In particular, this formula here can also be rewritten in the following fashion, and I will give you some more information about what I'm doing here. This integral, together with the factorial, can be combined so as to rewrite the formula like this. We have an integral from y0 to xt dx of tau exponential of im over 2 h bar integral from 0 to t x dot squared d tau. And then here you have to multiply this by the following integrals. So it's a series of integrals. So we have multiple integrals of the kind integral 0 to t d tau 1 integral from 0 to tau 1 d tau 2, and then you have integral from 0 to tau 2 d tau 3, and you get the idea. We have one last integral from 0 to tau k minus 1 d tau k, and then here you have products of differentials v of x of tau 1 And you have all these products all the way up to v of x of tau k, like this. And why can you do this? So why can you start here and reach this point? Well, it's due to the fact that an integral from 0 to t v of x of tau d tau can be shown to be, in particular the nth power of this, is equal to n factorial times integral from 0 to t d tau 1, integral from 0 to tau 1 d tau 2, dot dot dot, integral from 0 to tau k minus 1 d tau k, and then you have these differentials, v of x of tau 1, and then you have v of x of tau k. So this formula can be proved by induction, but I will give you just a simpler way of understanding this formula. So we will prove it quite intuitively, so it's not a rigorous derivation, but I think that this might allow you to understand a little bit better what's going on, why this is an actual equality. So discretize this integral first. You can write it as summation over j vj, let's write it like this for simplicity, to the power n. This can be written as, so when you raise this sum to the power n, you have n sums, so summation over j1, summation over j2, dot dot dot, summation over jn. So when you raise this sum to the power n, you can write a product of summations with different integer values to sum over. So you have vj1 dot, so it's a product, vj2 dot 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 vjn. But now, due to the symmetry of our problem, it's quite easy to understand that we can sum, and now I'm just writing one summation symbol for simplicity. You can sum over the following possibilities. So let's assume that j1 is greater than j2, which is greater than j3, which is greater than dot dot dot, which is greater than jn. You can understand that the order in which you write these indices is not important because you will get the same result. So basically this summation here can be performed over all such inequalities, but how many inequalities do we have? You have all the possible permutations of these indices. So you have n factorial of such summations, which will give you the initial summation here, and then of course you have vj1, vj2, dot dot dot, vjn. So this is the idea of how to understand this result, which allows you to rewrite this function g sub k in this manner here. And formally, you can rewrite this result, so g sub k can be rewritten by means of the following integral. Now, I will explain this as well. So you can integrate from 0 to t d tau, integral over xi, defined like I did earlier. Then you have g0 xt xi tau. Here you have v of xi, but now you have to be a little careful because here you have to define, so you have to write, instead of g0 as we did earlier, we have g sub k minus 1 of xi tau y0. So this is quite formal, but it can be explained quite easily because g sub k minus 1 contains k minus 1 times such terms, the terms related to the potential. So there are k minus 1 times potentials in here, and so therefore this function explains k minus 1 interactions at k minus 1 different points, but after that you have another interaction at the final point here, so at the point xi, and in principle this differential could also depend on time. So it could be v of xi tau if you want to be more general. Now I'm assuming that the potential only depends on space, so it is a function of this final point. And after that, we have a free propagation from this point to this point here because there are no other potential terms after this one. So this is the idea. And I think that this is a powerful idea because now we are approaching the moment in which we are going to describe Feynman diagrams. We really have all the tools to be able to understand what's really going on pictorially, just like Feynman did in his studies. So he understood that the path integral can be reformulated pictorially in terms of visual representations of interactions. By keeping track of the definitions that we gave of the terms g sub k minus 1, g sub k, and so on and so forth, it is quite straightforward to write down the following equation: g of x t y 0, which is, remember that this is the total propagator, the first thing that we wrote in this video, and in particular we wrote it as a sum. If you remember, this is a series of terms, j from 0 to infinity minus I over h bar j, g sub j, xt y0, and we also found some equations that this gj should satisfy, starting from the path integral formulation, and it is quite straightforward to write down also the following equation for g of xt y0 should be equal to g0 of xt y0, which is also the first term that you have in this expansion. So if you set j equal to 0, you basically get this. But you can write the other terms that come after the first one here like this: minus I over h bar integral from 0 to t d tau integral d xi g0 xt xi tau. Then here you have the potential at xi, and here you have the total propagator xi tau y0. So it is quite straightforward to arrive at this expression, remembering all the conditions that should be satisfied by such terms. And this expression here might seem strange, but actually, if you remember the fact that G0 satisfies the Schrödinger equation with those Dirac deltas, it is quite straightforward to understand and to show that G satisfies the following Schrödinger equation: I h bar d over dt plus h bar squared divided by 2m d squared dx squared. Then you have minus the potential evaluated at x acting on the function itself, g xt y0. This would be equal to I h bar delta of x minus y delta of t. So this is basically the non-free version of the Schrödinger equation, because we also have the potential energy here for the total propagator. Now we are really arrived at the final part of this lecture. In particular, for example, if we consider the interactions of first order, so the interaction of zero order here would be the free propagation, as we have already understood earlier, because we don't have any contribution related to this potential energy. But, for example, G sub 1, how can we pictorially represent such a term? So if we draw the arrow of time here, and we start at the point y at time t equal to 0, we can draw a line, which is a propagation, a free propagation up to the point xi tau. If you recall, this xi tau appears as an intermediate step between this point and this final point here. So you have xi tau at time t equal to tau, point xi. So here you have some kind of interaction with the potential at xi, and then you have a final free propagation to the point xt. So this is the interaction of first order. But similarly, you can represent a pictorial graph for G2. Here, if you have the arrow of time, so we are moving forward in time here, we start at the point y0, then we propagate freely until we reach the point, let's say, era sigma, where we have the interaction with the potential v at the space point, let's say, era. Then you have a free propagation until we reach the point xi tau. So here we have an interaction with the potential v of xi. And finally, we have a final propagation until we reach the point xt. So here we have two interactions that occur at these intermediate points. And remember that we are really integrating over these variables xi tau and era sigma. So it means that we don't really know when and where these interactions are occurring, because we are really integrating over all the possible values where and when those interactions occur. This is due simply to the probabilistic interpretation of the path integral, which is related to quantum mechanics.